All right, last but definitely not least, we come to example 4. And it's the last example on here. And so naturally, it's probably the most difficult. Okay, so notice here that it's asking us now to estimate a volume. So we have now a third dimension. And you might be wondering where the third dimension comes from, because we have this curve here, which, by the way, is a half circle. So just note to self, every time you have an equation of this form, which is the square root of r squared minus x squared, r of course being a number, that's a half circle. So in this scenario, our radius is 4. And so that's why it goes right here at 4 and right there at 4. And actually, it should continue all the way over here at 4. But we are only partitioning from 0 to 4, which is why we leave off the negative side. So then you might be wondering what the heck is going on down here, because it's supposed to just be between this curve and the x-axis. That's how these problems work. Well, basically what's happened is we started off with a half circle and then rotated it around the x-axis. So you're probably wondering what that looks like. So I'm going to zoom out here for a second. Or yeah, just kidding, zoom out. And so here I have a half circle. So imagine this is the x-axis from 0 to 4. This is the y-axis 0 to 4. This is my x-axis. Okay, so this is what we had right here. But then I'm going to rotate this 360 degrees around the x-axis, and lo and behold, I now have a three-dimensional object because of that rotation. Okay, and don't laugh at my like my party thing that's like falling apart. But anyways, here we have this. So I need you to envision, we're looking at this from the side. We're looking at it from the side, but it's actually a three-dimensional object, which is why we are searching for a volume. Also, notice this is a half sphere. So the volume that's been created is a half sphere. And I'm looking at this half sphere from one direction, so it looks flat, but really no, it's three-dimensional. And when you cut a half sphere into sections or cross sections, those cross sections are going to be cylinders based on the circular cross sections of this half sphere. So you're probably wondering, why don't you just use the formula for a half sphere? And the answer is because. So we'll check our answer with the formula, but because we're learning about how to use calculus to find these kinds of volumes, because there's going to be times in our life when they aren't perfect shapes like this, and so we're going to need to use another method. So for right now, we're using easy shapes that we can kind of know the formulas for and check our answers, so that when we get to the more difficult contexts, we'll be ready for them. Okay, but let's go ahead and do this. So visualize these as cylinders that are standing up. So something kind of like this. Okay, sorry, you have to pardon my like extremely rough sketches here. And the radius is of course from the center to the edge would be the radius. And so notice these radiuses or these radii are standing straight up. So in this scenario, the way we're going to find the radius is by using the y values, because these cylinders are standing up. And so just really quick, the volume for a cylinder is pi r squared h. So the radius values are these guys right here. They're the heights, or the y values, if you will. And then the h is actually, since this is actually like a on its side, so to speak, what's usually the height of the cylinder is now sort of the width of the cylinder. And the way we're going to determine that will be the distance between x values. So let me see if I can draw a better picture of the cylinder. Maybe I'll just make this come a little closer here. I don't know if that helps or not. Anyway, so normally we're used to cylinders that are like flat like that. And so that's why we call that one the height, and then the radius is like that. And it's like you took this and stood it on its side. so to speak. And so these are like 8 different size cylinders with the radius going straight up, and then the heights are like the distances between x values. And it tells us to break that into 8, somewhere it said 8, here it is, 8 subintervals of equal length, which this picture has already done for us actually. So we have right here is 1/2, 1, 1.5, 2, 2.5, 3, 3.5, 4. Okay, so I basically just need to find the volumes. I need to use this formula for 8 different cylinders. And notice that, again, the height of the cylinder, which is the distance between x, is the same for all of these because I split them into halves. So each of those like heights or bases or whatever you want to call it is 1/2 for each of them. Now the radiuses are going to be different. The radii are going to have different values depending on this equation, but the heights are all the same. Okay, so the way you find the radius, or the radii, is by taking those endpoints and plugging them into this equation. And so notice this one asks specifically for left endpoints. So like the first radius, I would use 0 and plug it in there. So for the first radius, I would get 16 minus 0 squared. And so that would be the square root of 16, which is 4. For the second radius, I would use this left endpoint for this interval of 1/2. And so I would do 16 minus 1/2 squared, which is 16 minus 1/4. And you end up getting a decimal for that. And that decimal ends up being a big number. It's basically the square root of 15.75, and so on. Okay, so that's how you would find all your different radii. And then as far as finding the volume using left endpoints, the formula would basically go like this. It's going to be pi times r squared times h, which is 1/2 for all of them. And the way, again, that you find r is by plugging the different endpoints into this equation. So maybe I'll call this equation f of x, so that what I do next makes sense. So like this would be f of 0, and then square that. And then you would do pi times f of 1/2, f of 0.5, square that, and then times 1/2. And then pi times f of 1, square that, times 1/2. And so on and so forth. So f of 1.5, square that, times 1/2. Pi times f of 2, square that, times 1/2. Pi times f of 2.5, square that, times 1/2. And then pi times f of 3, square that, times 1/2. Pi times f of 3.5, square that, times 1/2. And those are all the left endpoints. So I should have 8 altogether. 1, 2, 3, 4, 5, 6, 7, 8. So I do. Also notice that I had to write pi and 1/2 and pi and 1/2 every time. If you wanted, you don't have to write them every time. You can just sort of have them factored out off to the side, like this, pi times 1/2 times, and then you would just have all the radiuses squared, f of 0 squared, f of 1/2 squared, and so on and so forth. And so after you do all of those calculations, by plugging in the numbers like I did here, and then squaring them, and then multiplying by pi and 1/2, you would end up with 146.0841. And then that's units cubed, because we were finding a volume, because we have 3 dimensions, a radius squared, which gives 2 dimensions, times height, which gives the 3rd dimension. Okay, so then that's part A. For part B, you basically find the actual value of, or actual volume of this half sphere. So this is a half sphere. The actual volume of a half sphere, or of a whole sphere, is 4/3 pi r cubed. And then I would just need to divide that in 2, since it's a half sphere. And so I get 4/3 pi 4 cubed. So that would end up being 268.08, and then I would divide that in half and get that the actual volume is 134.04. So it turns out that our answer was an overestimate, and it's pretty obvious. You can kind of see from here, this function was decreasing, and so our rectangles went over, like above and beyond where they should have gone. So it's obvious that our answer would be an overestimate. And so to find the percentage of how much we were off, we would basically subtract these two. So maybe I'll do that right here. We would do 146.0841 minus 134.04. And I get 12.0441. I'm going to divide that by the actual to see how far off we were from the actual. And it turns out that we were only about 9% off. And then if we increased the number of cylinders to 50 or 100, we could get much closer, possibly to within 1%. So again, this is just sort of using simple geometry to estimate areas under curves, and in this scenario, areas of volumes after something, values of volumes after something's been rotated around the x-axis. So I will see you in class tomorrow. Please come into tutorial if you have any questions.